Have you ever felt the ground shake beneath your feet? It's a wild ride, right? Earthquakes are like the planet's way of letting off some steam. They're more than just natural disasters, though. They're like clues that help us understand what's going on deep inside our planet. Earthquakes tell us that our planet is constantly changing and moving. It's hard to believe when you're just walking around, but the ground beneath us is always shifting and groaning. And sometimes it just can't take the pressure anymore and bam, earthquake. But what causes these shakes that can topple buildings and reshape landscapes? Why do some areas of our planet seem to shake more than others? Get ready to dive deep as we explore the awesome forces that create earthquakes. To understand earthquakes, we need to take a peek beneath the surface, down into the heart of our planet. Imagine this. The Earth is like a giant onion. It's made up of layers, each one different from the last. The outermost layer, the one we call home, is called the crust. It's thin and brittle, kind of like an eggshell. The crust isn't one solid piece. It's broken up into massive chunks called tectonic plates. These plates are like giant puzzle pieces that fit together to make up the Earth's surface. And guess what? They're not just sitting still. They're constantly on the move, drifting and grinding against each other. Picture this. Massive tectonic plates, right? Continent-sized slabs of rock floating on molten goo. It's like a slow-motion demolition derby down there. A wild dance with three main moves: convergent, divergent, and transform. Let's talk about convergent boundaries, where tectonic plates collide head-on. It's the ultimate clash of titans, a slow-motion train wreck that can take millions of years to unfold. Imagine two massive freight trains barreling towards each other. What happens? A whole lot of energy is released. That's what happens at convergent boundaries. The immense pressure can push the land upwards, creating towering mountain ranges like the Himalayas. But it's not always about building mountains. Sometimes one plate gets forced beneath the other, diving down into the Earth's mantle. This is called subduction, and it's a recipe for some of the most powerful earthquakes on the planet. Now, let's switch gears and talk about divergent boundaries, where plates decide they've had enough of each other and start moving in opposite directions. Imagine the Earth cracking open, magma oozing up from the mantle to fill the void. That's what happens at divergent boundaries, and it's how new crust is formed. The Mid-Atlantic Ridge, a vast underwater mountain range that snakes its way down the center of the Atlantic Ocean, is a prime example of a divergent boundary. As plates pull apart at divergent boundaries, they create faults, or cracks in the Earth's crust. These faults can be kilometers long and are prone to earthquakes as the plates continue to move apart. Finally, we come to transform boundaries, where plates slide past each other horizontally. Imagine trying to move two pieces of sandpaper in opposite directions. It's not going to be smooth sailing. The friction between these plates creates immense stress, and when that stress exceeds the strength of the rocks, bam! Earthquake. The San Andreas Fault in California is a classic example of a transform boundary. This fault marks the boundary between the Pacific Plate and the North American Plate, which are sliding past each other at a rate of about 5 centimeters per year. That might not sound like much, but over millions of years, it adds up. Transform boundaries can produce some of the most destructive earthquakes, as the sideways movement of the plates creates intense shaking along the fault line. How does all that movement translate into the ground-shaking, city-rattling power of an earthquake? Imagine this. You've got these giant plates pushing, pulling, and grinding against each other. It's like trying to stuff a week's worth of laundry into a tiny suitcase. Something's gotta give. All that pushing and shoving creates immense pressure along the plate boundaries, like a pressure cooker about to blow its top. The rocks along these boundaries are under constant stress, but they're tough cookies. They can withstand a lot of pressure, but even the toughest rocks have their limits. Think of it like bending a twig. You can bend it, but eventually it's going to snap. That snap is what we call an earthquake. It's the sudden release of all that pent-up energy, radiating outwards from the breaking point in the form of seismic waves. What actually causes the rocks to finally give way? It all comes down to friction and faults. Faults act like giant scars. marking where the plates have moved past each other in the past. These faults aren't smooth like a freshly paved road. They're rough and jagged, and they're held together by friction, that force that prevents things from sliding easily. But as the plates keep moving and the pressure keeps building, the friction can only hold on for so long. It's like trying to start a fire by rubbing two sticks together. You have to apply enough pressure and overcome the friction to generate enough heat to ignite the flame. In the case of an earthquake, the flame is the sudden release of energy as the rocks along the fault finally slip past each other. That sudden release of energy sends shock waves through the earth, and those shock waves are what we experience as earthquakes. Think of it like a pebble dropped into a pond. The snapping rocks are the pebble, and the ripples are seismic waves traveling through the earth. How do we measure these seismic shakeups? How do we know where they start and how strong they are? That's where seismologists come in, armed with seismometers. Seismometers detect even the slightest shakes in the ground. When an earthquake strikes, it sends out those seismic waves. The P waves and S waves that zip through the earth like runners in a race. And who's waiting at the finish line? The seismometers. As the seismic waves pass through the earth, they cause the ground to vibrate, and these vibrations are picked up by the seismometers. The seismometer then records these vibrations as a series of squiggly lines on a seismogram, which is like a heartbeat monitor for the earth. By analyzing the seismograms from different locations, seismologists can pinpoint the earthquake's epicenter, which is the point on the Earth's surface directly above where the earthquake originated. How do we know if it was major earthquake? That's where earthquake magnitudes come in. Seismologists use the moment magnitude scale. It measures the size of the fault, the slip, and rock rigidity. The scale is logarithmic, meaning each whole number increase represents 10 times more energy. The previous earthquakes remind us of the devastating power and the importance of preparedness. Building codes have evolved, incorporating lessons from past earthquakes and advancements in engineering. Preparedness also includes early warning systems and public education. Each earthquake teaches us to build a more resilient future. Can we predict earthquakes? Well, not yet. But early warning systems are our best defense. They detect the first signs of an earthquake and send out alerts before the shaking starts. Every second counts. Building to withstand the architecture of resilience. Early warning systems are fantastic, but they're only part of the equation. Earthquake-resistant construction is the art and science of designing buildings that can dance with earthquakes. Think of it like martial artists, trained to move with the flow of energy. They're designed to absorb and dissipate seismic forces, protecting the people inside. Engineers use techniques like reinforced concrete, base isolation, and ductile detailing. These innovations create buildings that can withstand powerful earthquakes, protecting lives and minimizing damage. Earthquakes don't discriminate. They can strike anywhere, anytime. It's about coming together as a community to support each other and rebuild stronger. A single twig can snap easily, but a bundle of twigs bound together can withstand tremendous force. Our communities are like that bundle of twigs, stronger together. When the ground shakes, it's our connections to each other that help us emerge stronger. We've journeyed to the heart of our planet, explored the awesome forces that make the ground shake, and learned how to stay safe when the Earth decides to do the jitterbug. From the slow-motion dance of tectonic plates to the lightning-fast alerts of early warning systems, we've seen how science and technology are helping us understand and prepare for these seismic spectacles. But remember, living on a restless planet isn't just about bracing for impact. It's about respecting the raw power of nature, learning from its lessons, and building a future where we can coexist with these earth-shaking events. It's about appreciating the incredible forces that have shaped our planet over billions of years, from the towering mountains to the vast ocean basins. Earthquakes might shake us, but they also remind us that we're all connected to each other, to our communities, and to the dynamic planet we call home. So, let's keep exploring, keep learning, and keep building a more resilient future together. Fuel your curiosity, find your Nirvana.